want to approximate the length of curves. We'll do that by taking our parameterized curve. R of t is equal to f of t, g of t, for some t values between a and b. Now the horizontal component is given by the f of t. So our x-axis will have f of a and f of b is the endpoints of that interval from a to b. Now divide that interval into subintervals, and we'll look at each subinterval and we'll approximate the length of the curve it's right here. To do that, what we'll do is we'll take this curve, drop a perpendicular down from the highest point so that it's on the same level as the lower point. This horizontal distance is delta x sub k, and the vertical distance will be delta y sub k. The hypotenuse would be delta x sub k squared plus delta y sub k squared. So we'll use that for the length of the curve in that subinterval, sum up all of those curve lengths in each of the subintervals, and that's how we'll get the length of the curves. Okay, so now let's look at this expression and see if we can simplify it. I want to take this and I'm going to multiply through by delta t over delta t. Since I'm going to take one of the delta t's inside of the parentheses, I'll leave one of them outside. I'm going to have a delta t squared on the inside of the parentheses. So now summing up all of these values, the mean value theorem says that if we have a function, x of k, or f of t in this case, that there has to be a specific value in that interval that actually has that slope. So there is some t value in the subinterval, the t sub k subinterval, so that this value right here is f prime of some t sub k. Likewise, for the function g, there's some value in the interval where that slope of g will have this value, the delta y sub t over delta t. So we'll have g prime of t sub k squared. We still have our delta t sub k on the outside. And this leads us to our formula for finding the arc length of a parameterized curve. So consider a parameterized curve. This one's 3 dimensions, so we have an f, g, and h, where f prime, g prime, and h prime are continuous, and those are the derivatives. The curve is transversed for t between a and b. The arc length will be given by the square root of f prime t squared plus g prime of t squared plus h prime of t squared from a to b. Now notice that that is just the magnitude of the r prime. Remember, if r of t was just the f, g, and h, r prime of t was f prime, g prime, and h prime. So the magnitude of r prime was just the square root of f prime squared plus g prime squared plus h prime squared. So that's the arc length. So all we're doing is we're integrating magnitude of r prime of t times dt. Now we're finding the length here. Remember, this is just a speed, and this is just a time. So if you remember that distance equal to speed, rate times time, then you can see that this does make sense. Okay, I want to prove that the circumference of a circle is actually 2 pi times a if the radius is a. So what I need to do is I need to first find a function, r of t, that represents that circle of radius a. Now, if you remember from working with parametric equations, that a circle of radius a will have parametric equations a cosine of t, a sine of t, and the t values range from 0 to 2 pi. That will describe a circle of radius a. So now, the arc length we know is the integral of the magnitude of r prime of t dt from a to b. Now we don't have to actually integrate the circle from a to b from 0 to 2 pi. We could just do a fourth of it from 0 to pi over 2. So let's take 4 times the integral from 0 to pi over 2, and we need to find the r prime's magnitude. Well, if r is a cosine t, a sine t, r prime is negative a sine of t, a cosine of t. The magnitude of r prime will be the square root of a squared sine squared plus a squared cosine squared, which is simply just a when you factor it and remember that sine squared plus cosine squared is 1. So our integrand ends up being just a. So integrating a with respect to t, we get 4 times a times t from 0 to pi over 2, and we get that the length of that curve is 2 times a times pi. So that is just the circumference of a circle. Let's find the length of this hypocycloid that's given by this function. Well, we know arc length is the integral of the magnitude of r prime of t dt from a to b. Now again, I'm not going to integrate over the entire 0 to 2 pi. If I see symmetry, I want to take the smallest piece that I can. The reason for that is that sometimes on these functions, you could have some values that may not be positive for the function and it may not give you the right answer. So pick the smallest piece that you can use and then use symmetry to get the rest. So I'm going to go from 0 to pi over 2. I know what r is, so I need to find r prime. Now r, I'm going to rewrite this as cosine of t cubed and then sine of t cubed. So taking the derivative, I need the power rule. 3 cosine of t squared times the derivative of the inside, which is negative sine of t, and then 3 sine of t to 1 less power, so it's going to be squared, times the derivative of the sine of t. So I'm using the power rule and the chain rule. So that gives me negative 3 sine of t cosine squared of t, 3 sine squared of t cosine of t. And that's my r prime of t. So now, the magnitude of that will be the square root of 9 sine squared cosine to the 4th plus 9 sine to the 4th cosine squared. Okay, taking out common terms, we see that we have a 9 sine squared cosine squared in common. We'll have a cosine squared t plus a sine squared t left, which we know is just 1. So now we have the integral from 0 to pi over 2 of just 3 sine t cosine t. There's several ways to integrate this. One way is to recognize sine t cosine t, and you can change that to a double angle formula or a product to sum formula. The simplest thing here is probably to use a u substitution. I'm going to let u equal to sine of t. So du is equal to cosine of t. And so that takes care of this portion. So when you make the substitution, this is equivalent to 3u du. And now we need to change our limits of integration. When the t was 0, the u will be sine of 0, which is 0. And when the t is pi over 2, u would be sine of pi over 2, which is 1. So now, finishing the integration, we have 3u squared over 2 from 0 to 1, which just gives us 3/2. Now we just found a fourth of that, so the arc length here will be 4 times all these values, which ends up being just 6. So 6 units is the arc length of that hypocycloid. Now let's say that an eagle rises at a rate of 100 vertical feet per second on a helical path given by this function. R of t is 250 cosine t, 250 sine t, 100 t. So we've got a helix described by this function. Now r is measured in feet and t is measured in minutes. We want to know how far does it travel in 10 minutes, which means we want to find the arc length of the trajectory. Okay, so we have that the arc length will be the integral from a to b, the magnitude of the speed, which will be the integral from, it says in 10 minutes, so from 0 to 10. R prime is negative 250 sine t, 250 cosine t, 100. So the magnitude of that velocity function, which is its speed, will be 250 squared sine squared plus 250 squared cosine squared plus 100 squared. If we take the first two terms under the radical and factor out the 250 squared, we get sine squared plus cosine squared. So this becomes simply 250 squared plus 100 squared. Now 250 squared is actually 62500. So that is okay. Now that's approximately 269. So this will be the square root of 72500 times t from 0 to 10. So we'll have square root of 72500, which comes out to be approximately 2690 feet. And so that's the distance that that eagle would fly.